So I'll be talking about classical identification of emergent geometries. Well, in a way, CFT AdS is a kind of strong weak coupling, so in some sense, classical quantum correspondence. So in a way, one should probably expect to be able to relate classical algorithms to quantum algorithms, in classical algorithms in gravity to quantum algorithms in CFT. So this is a concrete realization of that based on these two papers with Joseph Bengeloun. And get the full screen view here. So this is going to be in the context of the simplest example of AdS CFT, string theory on AdS5 cross S5, which is dual to n equals 4 super Yang-Mills with UN gauge group in 4 dimensions. So it's emergent space-time, or emergent space at least. Well, certainly AdS structure is emergent, S5 is emergent. So this is an example well within the theme of this conference. So thanks for this invitation. And we're going to see how this setup for AdS CFT allows us to explore this connection between classical and quantum algorithms. So we're going to be looking at half-BPS operators. In CFT, these are described by taking two of the 6 Hermitian scalars in n equals 4 super Yang-Mills and forming a complex combination, Z, which could be x1 plus ix2. And we form gauge invariants. So these are the familiar gauge invariants, traces of powers of Z, traces of, for example, if you have 3 Zs, dimension 3 operators, you can have trace Z cubed, trace Z squared, trace Z, or trace Z the whole cubed. So very important, there's a hidden algebra in the description, in the kinematics and the dynamics of these gauge invariant operators. And this comes from the observation that these different trace structures are obtained by taking, let's say if you have dimension 3, you have 3 Zs, and the indices of the Zs are contracted in some way. And you can do that by labeling the indices I1, I2, I3. And then the lower indices, because this is a gauge invariant operator, they all have to be some repetitions of the above indices. But what order is not fixed by gauge invariance, rather there's a permutation that you could apply. So here you take the cyclic permutation, 1 goes to 2, 2 goes to 3, as a substitution rule. That's 1 goes to 2, 2 goes to 3, 3 goes to 1, and 1 goes to 2, 2 goes to 3, 3 goes to 1. So in this way, the order of the indices of the lower indices relative to the upper indices determines the gauge invariant operator. So here, therefore, this is contracted, so this is trace Z cubed. And if you take 1, 2, 3, and if you take 1, 2, the swap with 3 staying where it is, this is trace Z squared, trace Z. And this is the identity. So all the indices above and below are the same. So that's trace Z, the whole cube. So obviously, any gauge invariant operator can be obtained for any number of Zs by using an appropriate permutation in Sn. So that's a rather basic remark about how to build gauge invariant operators. Now, if you look at that formula, one thing becomes apparent, that if you take that sigma and you conjugate it by another gamma, an arbitrary gamma, you get the same gauge invariant. And that's kind of obvious because you see, you had 3, well, it's just a kind of playing around with relabeling indices and using the bosonic property of the Zs. That equation can be derived, but also you kind of expect this because with 3 Zs, there are only 3 operators you can build, but there are 6 permutations. So only the cycle structure matters, how these numbers are organized into cycles, and that cycle structures of permutations are also conjugacy classes. So that means that permutations which are conjugate related by some conjugation by some other gamma, give you the same operator. So given any cycle structure of this kind, so namely you specified how many one cycles your permutation has, how many two cycles it has, you get a corresponding operator with trace z to some power, z squared to some power, z to the n to some power, and so on, where this equation just tells you that the total number of z's is n. So we're fixing attention on all the operators of a fixed dimension n. So once you have an operator of a fixed dimension n, this multi-trace, you can also write it as, again, a trivial thing from the remark before, pick any permutation, sigma upper p, of that cycle structure, and use that to build this contracted operator. Great. But you could have picked any one of the permutations with that cycle structure. So because you could have picked any one of the permutations, you could actually sum over all of them. Any of the permutations with that cycle structure, you could sum them all up and divide by the number of permutations with that cycle structure. So already you see some very interesting structure here. Sums over permutations with some weight. Where do these things live mathematically? If you take an object like this, sums of permutations in a given conjugacy class with a weight, these live in the group algebra. So there's a very interesting algebra in the game, group algebra of Sn. And in particular, these kinds of sums where you are summing with over everything in a given conjugacy class with the same weight, they live in the center of Sn. So these things commute. So if you multiply by a gamma on the left, it's the same as multiplying by a gamma on the right. So these things live in the center of the group algebra. And as P, the partition, ranges over the partitions of N, these form a basis for the center of the group algebra. Great. There's another interesting basis for the center, for the same algebra, which is where you take sums over permutations, but you weight them with characters in some irreducible representation of Sn. And I have chosen these normalizations to make sure that these projectors multiply in this way. So they are orthogonal projectors. You multiply two of them, you get 0 if they are distinct, and you get just P if they are the same. So that's a projector equation. So that's a change of basis within the same algebra. We have gone from these basis of these T sub P's and to the basis of projectors. So the sure basis operators that you have heard about in earlier talks from David and Gautam as well are simply these multi-traces weighted by these characters, and these projectors, you see this sum, chi r sigma sub sigma, is exactly the kind of thing that is appearing in the formula for the projector. It's like the projector version, the operators, the Z operator version of this projector is what the Schur polynomial is. So, great. And using properties of this orthogonality of projectors that we just mentioned, you can prove this orthogonality property. So this is OROS, and there should be delta RS here, f of r. F of r is a very simple polynomial that depends on the Young diagram, and it's also related to dimensions of representations associated with that Young diagram. And that orthogonality relation, which was derived in this paper with Antal and Coley, that orthogonality relation follows very simply, very easily from the orthogonality of projectors. So it's just a matter of setting up the combinatorics in the right way, and you see this, and it follows from the algebra. So these calculations are effectively, although they are of physical interest in n equals 4 super Young-Mills, they are really calculations in complex matrix model, and you can actually generalize these calculations by putting an arbitrary matrix coupling here. So A is a Hermitian matrix, and in a recent paper, we explained how these formulae generalize when you introduce that background matrix. This f of r, this normalization factor, gets itself replaced by a Schur polynomial operator, which depends on that background matrix. This makes contact with the super integrability program of Mironov and Morozov. So this Young diagram basis, this R was a Young diagram, allows the identification of operators, of dual operators, which are related to semi-classical giants. Basically, long rows are related to giants, which are large in the AdS directions, long columns, giants, which are large in the S-sphere directions. And these has a nice connection to free fermions, as was elaborated in these papers. And as also David mentioned, there's extensive evidence for this picture of the connection between the Young diagrams and the semi-classical giants, developed in many papers that also make contact with sort of multi-matrix combinatorics. So, and beyond giants, there is another story, which is that if you have many giants, in other words, you have operators with dimension of order n square, then these giants deform space-time and you get deformations of space-time, and these large deformations of space-time with AdS5 cross S5 asymptotics were classified by Lin, Lunin, and Maldacena in 2004. And one of the things that they found is that the structure of these solutions is described neatly in terms of a two-dimensional plane embedded in this 10-dimensional space-time. And this two-dimensional plane can be related to free fermion phase space. These are capital N fermions in a one-dimensional harmonic oscillator, and colorings of the plane are related to sort of phase space states for this fermion system, and they also determine boundary conditions that determine the solution itself. So this is a rather remarkable connection between gravitational geometry and free fermions, which come about in the matrix model. So we're going to use all these little pieces. And what we're going to do is we're going to think about how to set up the question of, so the question we have in mind is somebody gives you one of these projectors, piece of bar, a Young diagram state, and what's a natural way to detect which one it is? And there's a natural algebraic way to do it. So we're going to talk about the algebraic way to do it as a problem in this Hilbert space. So I told you this is an algebra, the center of the group algebra. Turns out it is also a Hilbert space. It has a natural inner product. And there's an eigenvalue system that you can set up in this algebra, which will help you determine which of the projectors, which of the Young diagrams you've been given. And correspondingly, because these correspond to some classical geometries, there's also the question of determining which LLM geometry you have using properties of the metric. So in fact, people studied this question before, back in 2006, and that motivated the formulation of this algebraic problem that I'm going to describe. And once you've got the algebraic problem, turns out there's a nice way to set it up using a quantum algorithm, using very standard constructions in quantum information theory, and we can get complexity estimates, which are basically how many steps or how many gates and things do you need, and how does that grow as n, little n, the number of z's increases. Does it grow polynomially, or does it grow factorially, or exponentially? So I'm talking about Sn, so Sn has lots of rapidly growing numbers associated with it, but does this detection problem grow polynomially, or factorially, or exponentially? And we're going to use standard results in group theory and quantum information theory to get an answer. So we are taking an open mind. We're taking the simplest detection that we can find here. We get an estimate. We take the obvious detection and associated complexity that kind of comes up, and we will show you the result. They are sort of similar modulo certain assumptions that we can clarify, but we don't claim to know whether they ought to have been the same. I mean, this is the beginning of a discussion. So, okay, so the algebraic problem. So we have, how much time? Maybe another 20 minutes or something, right? So the algebraic problem. So we have these projectors in this center of the group algebra, and here's a natural eigenvalue system related to this. So there are two dual bases in this center of the group algebra of Sn, the projector basis and the cycle structure, the conjugacy class basis. If you take this conjugacy class basis operator element of the group algebra, multiply by the projector, you get back the projector with this eigenvalue, which is the character of that thing divided by the dimension of the corresponding representation of Sn. Just a fact from group theory. So P is a partition in general, but it'll turn out that partitions of special kind, where you have one cycle of length k and remaining cycles of length 1, these are all that we're going to be that are going to be important in this projector identification problem. This is because if you take these eigenvalues, these eigenvalues normalized character for tk, where tk is 2 cycle, 3 cycle, 4 cycle, up to n cycle. If you take these normalized characters and you tabulate them for all Young diagrams, that list is enough to distinguish the Young diagrams. That's what we proved in this paper with Gareth Kemp, who was a lecturer in Johannesburg. In fact, there's an interesting group theory, and this is important for large and asymptotics and such. Group theory shows you that, for example, if you're doing Sn with n equals 2, 3, 4, 5, or 7, it is enough to know the normalized character of the swaps, T2. And if you know that normalized character for a Young diagram and you list it over Young diagrams, all these numbers are distinct. So this by itself is enough. So eigenvalue of this guy is enough to distinguish the Young diagrams. If you want to go to higher n, you add to these 2 cycle operators, the 3 cycle guys. And with these two, you can distinguish the projectors up to 14. And for any general n, there is an interesting number which we call k star of n, T2, T3 up to tk star, which k star is the smallest number, that the place where you have to stop in this list to be able to still distinguish all the Young diagrams. And we did this numerically, and we found that for n equals 80, up to n equals 80, you need at most 6 of these, T2 up to T6. So great, so that's kind of a mechanism for saying that these eigenvalue problems are good ways to detect these projectors. So part 2, now detecting LLM geometries. These LLM geometries, the very interesting form of metric, 10-dimensional metric. 2 dimensions play a special role, I equals 1 to 2. There are some functions v and h and r. All these, r is just the radius. All these functions are determined by one function, u, of 2 variables. So there's a function of 3 variables, which is determined by its value on the y equals 0 plane. And this value on the plane is itself related to a Wigner's phase space distribution associated to the quantum many-body fermion state. This was all explained in this paper of Balasubramanian et al. In 2006. And the upshot of that is that there is one function of 2 variables, a rho and a theta, which has an expansion in rho, some radial coordinate in this 10-dimensional space, times some function of theta, and then the coefficients of that are related to Casimirs of un. That's what BGLS 2006 explained. So in other words, the multiple moments of this u function know about the Casimirs of un. So you have a Young diagram, you have a representation of un, you have a Casimir, and the Casimirs of the representation are related. So of course, and the representation is a fermion state. The fermion state is an LLM geometry. So the LLM geometry knows about that Casimir, that sequence of Casimirs. And the more powers, the coefficients of more powers of rho you know, the more Casimirs you know. So what BGLS said is that, before I get to that, yeah, so these coefficients are Casimirs. Now, just to relate to this algebra introduced before, these Casimirs, like the quadratic Casimir of un, can be expressed in terms of these 2 cycle operators. And the analogous equations, C3 in terms of 3 cycles, C4 in terms of 2, 3, and 4 cycles, something like that. The upshot is, if you know the Casimir, if you know these normalized characters for T2 up to Tk, you can also figure out from these Casimirs, UN Casimirs, for C2 up to Ck. Just like here, if you know T2, there's a simple equation that figures out the quadratic Casimir. And this is all part of this general relation between UN representation theory and Chauval duality, which relates UN representation theory to representations of Sn for all possible n's. This little n is basically related to the number of boxes in your Young diagram. And it also tells you how Casimirs and these central elements are related. So the point made in this BGLS 2006 paper was that determining a general Young diagram and corresponding LLM geometry requires, if you just don't think too hard, you say, to determine a representation of UN, you need n Casimirs. But you know, the n, the sort of the Casimir, quadratic and higher Casimirs, so sort of, if you look at that formula, basically you would need to know CL for up to n. And they argued that, you know, by looking at the formula for U, that would require knowing information up to Planck scale or beyond Planck scale. And they interpreted it as information, a kind of information loss. So somehow the measurable, observable semi-classical things don't give you enough information to figure out the quantum state. But we can get back to that later. But underlying here, there's this interesting algebraic problem. You are given Young diagrams with little n boxes with a cutoff having no more than capital N rows. How many Casimirs exactly do you need? What's the minimum number of Casimirs you need? Of course, if you don't put any restriction on little n, you need capital N Casimirs. That's a standard result. But if you put some restriction on little n, well, what exactly is the number? So it's a very interesting number, just basic group theory, which is not known in general. So we're going to be talking about this problem where little n is less than capital N, and this is a number that doesn't depend on capital N because we're kind of in the large n limit, and there's this number k star of n, which is crucial. And I told you that k star of n for n equals 80 is 6. So it's a very interesting number. You can work it out, you know, computationally. Oh, that was sort of their argument. It's a kind of AdS CFT argument that, you know, Planck scale, if you use the formula for the radius and so on, 1 over r. Let me not get into that in detail. We can talk about it later. Great. So the task of identifying then, so I'm going to get back to the algebraic side, which is particularly motivated by this Casimir and multiple moment story. So the question now is how many of these, so we are given, you know, a projector, we're going to use these TK eigenvalue equations, and we're going to need T2, T3 up to K star. So, and you have a complicated state in group algebra of Sn, n can be very large, and what's the complexity of determining which projector it is? So we've observed that these eigenvalue equations are a good way to do it. Quantum information theory comes along and says, great, all you have to do is use the quantum phase estimation. It's a known technique. What you do is it involves putting in the TKs, exponentiating it. There's an appropriate normalization in the exponential. And you apply these unitary operators to the projector. You get a phase times that projector. And there is a way of figuring out, using a quantum circuit, that involves application of this UK. There's a way of figuring out what that eigenvalue is. So PR is a quantum, so you know, PR lives in the center of the group algebra of Sn, an algebra that I've defined, which is also a Hilbert space. So you're given a complicated state in that Hilbert space, which is PR. And you have available these TKs, which are combinatorial things, which we assume they're given to you. So you're going to take the TK, apply it to the state, find the eigenvalue, and then look at which eigenvalues they were. And this will help you identify which PR it is. And there's a quantum algorithm to do that, which is quantum phase estimation. And this comes along with some standard results of, something called query complexity. So in this way, we assume that these unitary operators are given to you as black boxes, and you're going to apply them. And there's a question of how many times you're going to apply these black boxes. And there'll be some other, and that's the query complexity. And there's a gate complexity, which involves the other things that you have, the other gates that are in the circuit. So this is from standard textbooks. You have the quantum state of interest. There's a bunch of register states, and the number of these register states depends on the accuracy with which you need to know this eigenvalue. And there's a bunch of Hadamard gates and powers of U, and then there's a inverse Fourier transform, which involves, again, Hadamard gates and rotations and some known stuff. No need to get into the details of that. Important thing is that there is a quantum phase estimation algorithm, and it is known that the query complexity is order T, the gate complexity is order T square, where T is the number of bits that you need in order to figure out the number of bits needed to record your eigenvalue. But your eigenvalues are known things. They are these characters. And there are known formulas for these characters. It turns out that it is also known that this is an integer. So you know that it is an integer, and you know that as R ranges over all possible Young diagrams, what is the maximum value and the minimum value. So there's a range of integers you're interested in. So therefore, you know how many bits you're interested in as a function of n. And k ranges from 2 up to k star. And we gave an argument that k star of n scales in the large n limit like n to the alpha, where alpha is less than 1/2 and bigger than 1/4. So the details of these estimates are in the paper. So basically some estimate, group theoretic estimates. So we use the results from gate complexity, query complexity for quantum phase estimation, and some SN group theory estimates. We find query complexity n to the 2 alpha, n to the 3 alpha, n log n. There's an n times log n and alpha. Alpha is a number between 1/4 and 1/2 in our calculation. So this is bounded by polynomials. So this problem of projector identification is bounded by n cube, let's say. Although Sn is something that grows like n factorial, the dimension of that algebra is the number of partitions of n, which is e to the root n. So this projector detection is fairly efficient. And so remarkably, because of AdS CFT, the same problem of identifying the Young diagram is a problem of identifying which LLM geometry you're given. And BGLS 2006 have told us that if you look at this function u of rho and theta, which determines the geometry, you can identify Casimirs and we know for fixed n, you need k star of n, Casimirs up to a cutoff k star of n equals n to the alpha. So in this paper, we also described how to go from measurements of u to calculation of the Casimirs. So given the existing formulae for LLM and BGLS 2006, there are some formulae for u in terms of these Casimirs and powers of rho and a function of theta. Let me not get into the details, but this formula can be simplified, and I've put in a cutoff lambda here because we are assuming that these angular momenta can be measured up to a certain cutoff lambda, which is the same k star of n, which is n to the alpha. So something, again, n-dependent. And simple manipulation, this is an expansion in powers of e to the 2i theta. And there's some coefficient here, and that coefficient itself is expressed. So this kind of directly knows about the Casimirs, and then there's some coefficients of Jacobi polynomials, something like that. So what you have to do is take the values of u on a circle, do an inverse Fourier transform to determine this. That's a fast Fourier transform algorithm, which is the best way to do it, that is known. And then knowing these, you have to invert this system, and you can estimate how many steps it takes to invert the system, and you can get an answer. Oh, great, actually it's more than I thought. So the physical input in this algorithm, so the algorithm is going to be a fast Fourier transform and then linear system inversion. Then the physical input is a set of values of u of rho theta. And theta goes from 0 to pi, and if you want angular momenta up to a scale lambda, you need to discretize this with order lambda points. So then we have this, this function of u of rho theta. So we kind of, I mean, this is a bit of gray area which we don't fully understand, but what is the computational complexity of measuring that many points of u? This is somehow to be extracted from the metric or fields in the LLM geometry. So we just kind of parameterize that as an unknown thing we don't know. So it's C of lambda. Okay, so this is a complexity of measuring u tilde at these separations, and there are lambda measurements because there are lambda places you have to measure. So lambda times this intrinsic complexity. And then there's a complexity associated with linear inversion of that linear system. I think that's lambda square, and complexity associated with that inverse or fast Fourier transform. So you can kind of bound the complexity, the obvious complexities that appear in this inversion problem. And remember, lambda is k star of n, which is n to the alpha. And alpha is some number, so less than 1/2. So n to the alpha, you put that here. Let's say this is bounded by n square, certainly. N square log of n, so bounded by polynomials. So if this intrinsic complexity is also bounded by polynomials in lambda, then this whole thing is bounded by polynomials in lambda, polynomials in n. Because lambda is n to the alpha, alpha is up to 1/2. So this is bounded by polynomials. Just like the quantum detection algorithm, bounded by polynomials in n. So now, when quantum information theorists think about this kind of linear, so this was partly inspired by Harrow, Hasidim, and Lloyd, who were the first back in 2009 or 11 or something, to start thinking about, can we use quantum algorithms to solve linear algebra problems more efficiently? So quantum mechanics is largely about matrices. So if you've got linear systems, can you solve them more efficiently using quantum algorithms? And they identified some algebra problems that, linear algebra problems that they could indeed solve exponentially faster than any known classical algorithm at the time. But then a few years later came along this paper called Quantum-Inspired Classical Algorithms. So these were kind of algorithms that were inspired by quantum physics, but they put in some randomness that simulates the kind of randomness, just like kind of some algorithms that use random number generators, but in a way that is inspired by quantum physics. So this found that you got pretty comparable results to the quantum algorithms of HHL, and this was in the context of recommendation systems. So recommendation systems have to do with how Netflix knows what programs you have watched, and it also knows all the programs that have been watched by many other people, and it wants to predict what programs it should suggest to you. I thought, okay, maybe I haven't read it as carefully as I should. It was, at least comparable. And, but an important part in that story was that, the data there was classical, and there was a step of converting classical data into quantum vectors. But our problem is kind of intrinsically a quantum problem. It's an eigenvalue problem to begin with. So it's not too surprising that we are finding, the quantum algorithm. Oh, so sorry. So we also did a kind of algorithm of this kind for our projector detection problem. And we found that that algorithm was a lot worse than the QPE quantum phase estimation. I don't claim that we did the best possible version of this, but we have something to start discussing. Anyway, so our version was that this kind of algorithm didn't work so well, but the holographic one worked almost as well. And modulo this assumption that this intrinsic measurement of the... Exactly, yeah. So modulo the unknown of how exactly do you quantify the complexity of measuring U from the metric. So that's the story. So to summarize, we've defined a quantum detection of projectors in algebras task. So very general associative algebras, whether they're commutative or non-commutative, they always have a projector-like basis. And so you can formulate the projectors, and very often the algebras of interest in AdS CFT, the algebras related to one matrix problems, two matrix problems, or tensor invariant problems. All these algebras have also a nice combinatorial basis, like cycles of permutations, graphs, or something like that. So there's a combinatorial basis of something like the TKs, and there's a projector basis, which is a group theoretic thing. And given this group theoretic thing, what is the complexity of measuring it using these eigenvalue systems? So we define this class of problems. We also got some estimates for some algebras related to multi-matrix problems, and these algebras are also related to the mathematics of Littlewood-Richardson coefficients, and some algebras related to tensor models, which are related to Kronecker coefficients. And so in fact, our work of Kronecker coefficients and tensor model motivated this kind of investigation. And in particular, but a lot of what we did concretely, the problem we defined is very much inspired by LLM, AdS5 CFT4. And so I guess this is all a proof of concept that one can make comparisons between quantum detection on the CFT side and classical detection on the geometry. And there are more refined questions you could ask, which I think are very interesting. In the quantum side, there was a query complexity versus a gate complexity. Are there analogs of that on the classical gravity side? This intrinsic unknown complexity that I introduced, how do we work it out? And it would be interesting to explore similar classical quantum comparisons motivated by AdS CFT or holography. And not just AdS CFT, but also whenever you have a classical geometry quantum state correspondence, which is the kind of thing that we also have in Matour's program, quantum state in AdS, in some orbifold CFT, geometry related to that large quantum state. You can think about detecting that quantum state using some kind of probes in gravity, analogous probes in the CFT. So I hope this is the start of a discussion about complexity comparisons for concrete, well-defined tasks, which are the same on the AdS side and the CFT side because of the AdS CFT dictionary. So I'll stop here.